good evening, everybody. Welcome to Ask a Meteorologist. We're going to try to answer just a few of your questions about weather. For those that do not know me, I'm a CFI and former National Weather Service research meteorologist. I'm also a contributing editor for Flying Magazine, so you'll see some of my articles in that magazine if you read it. And I'm also the founder of EZWxBrief, a progressive web app to do pre-flight planning. And I'm also the author of the SCUT Log PME, a primer for pilots that's both available in ebook and softcover format. But first of all, we're going to talk about surface forecast, surface features. So one of the questions I received was, what is a cold front, a warm front, and an occluded front? And specifically, the question I get asked a lot is, what is a surface pressure trough? Also, we're going to talk about what does it mean when there's an area of low pressure or high pressure represented on these charts? Also, what does it mean when the contours or isobars are close together or spread apart? Well, first of all, let's take and do a kind of an overview of some of the features you're going to see on these various charts, whether it's a surface analysis chart depicting conditions that happened in the recent past, or a surface forecast chart, such as a prog chart. So we're going to discuss the reasons we have these features presented on these two different charts. Well, first of all, let's look at frontal systems and frontal boundaries. Basically, anytime you see a front representing on these charts, that basically indicates that there are multiple air masses, and where those two air masses touch, that's essentially where you're going to see the frontal system. And so an air mass is one that has a consistent temperature and moisture profile across the line of latitude. So if you pick a line of latitude here and look at the general profile of the temperature and moisture, tends to be pretty much the same within that air mass. So we might have a cold and dry air mass to the north and a warm and moist air mass to the south. And where they meet in between, where they butt up against each other, that's where you'll find the frontal system. So why are there air masses in the first place? What is an air mass? Well, the easy answer is Mother Nature abhors extremes. So we know that there's cold air up near the poles and warm air near the tropics. And as a result of that, this kind of differential heating throughout our globe creates an imbalance that Mother Nature doesn't like. So it's all about this differential heating that occurs, and then Mother Nature attempts to bring that back to a balance. So to reduce or eliminate that imbalance that's out there due to the unequal heating of the Earth, she'll bring down cold air from the poles and move warm air up from the tropics. Sort of like a weather shell game that she's playing in order to bring things back to that equilibrium. And so this differential heating that we see creates what meteorologists call, very fancy term, but it's called baroclinic instability. And if you look aloft up in the atmosphere, all of the shell game is not just played at the surface, but it's also played at higher altitudes aloft. So if we have in this case, let's say our jet stream moving through west to east across the country, what you're going to notice is that these areas where you see a trough or a dip in the jet stream, that's cold air being brought down from the poles. The opposite is true where you see a ridge, that is warm air being brought up from the tropics. And it's this kind of mechanism that creates our major weather systems that we see on prog charts and surface analysis charts. And of course, where those two air masses collide and come together, that's what we see as a frontal boundary. And if you were to look at how the wind essentially maps to those frontal boundaries, you'll notice that where there's a front, there's an area of convergence. So you're bringing the cooler, dry air, perhaps, down on the western or northwestern end of that front, and then the warm, moist air up from the Gulf of Mexico. And where they meet here is that area of convergence. And so if you have weather that's, air that's converging at the surface, it has nowhere to go but up. And so frontal boundaries are basically places where we see air converging. So when you see a cold front on these charts, that means the cold air mass is on the move. And of course, when you see a warm front, that means the warm air mass is actually on the move. And we know that in reality, all these air masses are kind of moving together, but essentially the cold front defines where the cold air is moving into the warm air. And then a warm front defines where that warm air is moving up into the cold air. A stationary front is simply just that. Air masses are not moving, they're stagnant. And the one that's the most difficult one to explain to pilots is an occluded front. And essentially, an occluded front, it simply implies that one air mass is willfully taking over the other. And there are two types of occlusions. There's a cold air and warm air occlusion. Not to really have to worry about that a whole lot, but essentially when you see an occluded front on a chart, you know that that particular weather system is reaching its maturity. So typically we see a weather system go through this occlusion process, no different than when we see a wave in the distance that's ready to eventually crash onto the beach. As the wave is further out and eventually gets to a point where it curls and crashes onto the beach, think of that as kind of the occluded front. Essentially, it's reaching its maximum or it's reaching its maturity at that point and eventually will dissipate. So it's kind of the first point where the weather system reaches its maturity and then trends towards dissipation. So the movement of these air masses is generally controlled by these pressure systems that we have, highs and lows. So a low pressure typically develops on this pressure trough between air masses. So when you have an air mass butting up against another, essentially it creates a pressure trough, just like you would dig a trough in the backyard to bury a pipe. Same kind of principle. And essentially, if you were to pour water on each side of that trough that you dug in your backyard, the water would essentially sink to the lowest point in that trough and then eventually converge and move upwards. So as that happens, you can only imagine that there's going to be some swirls in that area where the water is flowing down into that trough. Same thing happens in the air. As that air converges together between those two air masses, in some cases, we can get that air to move and then finally develop into a circulation, and that's the area of low pressure. And so we get pressure systems because of that hemispheric imbalance I just talked about, mainly driven by temperature. So we know that temperature differences across the front drive pressure. Temperature differences drive pressure differences that ultimately drive the wind. And we know that air always moves from high to low. And that creates the circulation that we see in the form of areas of low pressure and high pressure. Now, the question I get a lot is, should I care about a frontal system? Well, some fronts actually have a lot of severe weather associated with it, have a lot of clouds, potentially low visibility, lowered ceilings, strong and gusty winds, possible severe turbulence, icing, all that may be in and around these areas of frontal systems out there. But in some cases, some fronts can actually be cloud free, can contain unlimited visibility and be actually quite benign. I see this a lot along the eastern US. I live in the Charlotte area. And it's not often, but sometimes we can get a frontal system come through. And the only big thing that you notice is really that it got actually, hot, hazy, hot, and humid before that front went through, to still being pretty warm, but being very dry on the other side of it, because a frontal system like a cold front is not only a temperature difference, but it's also a moisture difference across that boundary. And so one day it can be really hot and humid, and the next day be warm and pretty dry and tolerable. And so really it depends on the front, how much moisture it has to work with, and all the other aspects of that, what's happening with that weather system, that will drive whether it's a pretty significant system that has a lot of issues with it or one that has very few. So the area of low pressure that develops actually can be quite intense and produce significant adverse weather. Anytime you see an area of low pressure with a lot of concentric isobars around it, that means essentially that this is a pretty significant area of low pressure and therefore likely has a fair amount of weather associated with it. When it gets to be this strong, you can't help but most of the time have to deal with some significant low ceilings, visibility issues, certainly the possibility of convection or thunderstorms, and the possibility of turbulence in and around this particular low pressure system. And especially as you can see, this particular area of low pressure is actually going through the occlusion process here. And I know it's maybe a little bit difficult for you to see, but it's actually a dashed occluded front, which means it's actually in the process of dissipating. So this particular weather system has actually kind of reached its maximum in terms of its maturity and is trending towards dissipation. So anytime you see isobars that are generally packed pretty close together, that means you have a very high pressure gradient. It means the pressure changes rapidly over a given set of distance. And usually, but not always, you'll get really strong surface winds when you see that happen. So in many cases, in most situations, when those isobars are packed close together, what you're going to end up seeing typically is not only strong prevailing winds, but also some wind gusts that tend to be part of this. But there are exceptions to that. When you're looking at a high pressure, on the other hand, usually that's associated with fair weather. But in some cases, high pressure actually essentially provides a situation where there's subsidence or sinking air. And if there's kind of the situation where you have clear skies and calm winds in the overnight hours, that can actually be conducive for ground fog, radiation fog that's occurring as a result of that. So while high pressures are generally associated with fair weather, they can also be associated with some pretty intense radiation fog, some of the most thick fog that you'll ever experience. So just because there's a big old H there in the forecast doesn't necessarily mean that you're going to be dealing with in this case, because you can see all these station models here, which we'll talk about in a bit, are all filled in, which means you've got overcast skies, and essentially you're dealing with the possibility of low ceilings, low visibility, and the possibility of fog in those regions. So in the case where you see some of these isobars pretty far apart, you can see here that there's one isobar around the high, but it's really far apart from everywhere else. Usually you're dealing, for the most part, with pretty calm winds. You can see in this particular case, there's a circle with a circle around it. That means that the winds are calm there. Or you'll see a wind barb with a little half or a 5-knot wind barb in that particular case. So we're talking about, again, very light and variable winds. But there are cases where you can see weak pressure gradient and still have pretty strong gusty winds. So and we'll get to an example of that in just a bit. So all of this is fine, and certainly I'd like to be able to have every pilot understand all these kind of details and learn how to put them all together, but it's still a good idea to take and look at the prog chart and look at the weather type that's depicted here. You see that here on the left, and look at that in relationship to what you see listed here for the areas of low pressure, the high pressure, as well as essentially all the frontal systems. This kind of tells the story. The precipitation type that's shown here on the prog charts tell you the story of kind of what to expect. You'll also want to look at the convective outlooks. You want to look at other forecasts, such as the terminal forecast. You want to look at all the icing and turbulence charts. So you really have to put the big picture together, not necessarily just looking at highs and lows. But again, look at that as well. Look at the weather type as well as all this other information to get a better understanding of what this particular front's going to do and whether or not you're going to have your lesson the very next day. So I mentioned I want to specifically talk about a surface pressure trough. It's probably one of the most common questions I get on these charts. They see a dashed line and they don't really know what that means to them. So we're going to talk about a surface pressure trough. But first, let's do a quick review of some of the things we've talked about already in relationship to what you see on the surface analysis or even the prog charts. So on these charts, you're going to see over a dozen different kinds of symbols. And each symbol has a specific meaning that may or may not be important to you, depending on the situation. So one of the things you'll see on some of these charts, especially the surface analysis chart, you'll see these things called station models, essentially. And those are there to tell you in a graphical form, if you will, what the surface observation is at that particular station, or typically in this case, it's usually an airport. The way they design this is that in the upper left, you'll see the temperature. The lower left, you'll see the dew point temperature. Then you'll have the pressure. So this is 1,010.7 millibars. You'll see the weather type. In this case, it's showing moderate rain. They'll fill in the sky cover. Unusual to have moderate rain with clear skies, but normally this would be set up to have a quarter out for scattered, or it would have 3/4 for broken or completely filled in for overcast. And then you have your wind speed and direction with your wind barb. And the other thing, which I spend a lot of time looking at here, is the pressure trend. So this says it's 0.6 millibars over a 3-hour period, and it's falling. In fact, it has a little trend symbol here where it's been falling and then being essentially gone steady at that point. So it helps you understand in an area, you want to pay attention to that, because when you see pressure falling, typically that means the frontal system or weather is moving toward you. You like to kind of see pressure rising, on the other hand, which tends to tell you that weather is improving in that region. You also see surface pressure centers, whether it's a high pressure or low pressure that you see here, that will be depicted on the chart. Again, that's the pressure center, the highest or lowest pressure in the area. You'll see lines of constant pressure, or isobars, shown here. There's also, to really confuse you on some of these charts, they will actually put intermediate isobars, unfortunately, that are dashed. Basically, isobars are presented every 4 millibars. When there's weak pressure gradient, a lot of times the forecasters will pen in there, if you will, an intermediate isobar every 2 millibars. You also may see something like a squall line, 2 dots and a dash in front, typically ahead of a front. That's where we usually see that, but that'll be depicted there. And that indicates typically that you'll have some kind of severe convection that's producing very strong and gusty straight line winds in ahead of that squall line. You may also see something that's labeled outflow boundary. Looks a lot like a trough, but you'll see a little label ahead of that called outflow boundary right next to it. And essentially, an outflow boundary is the exhaust from thunderstorms. So if you had a large area of thunderstorms develop, the exhaust or outflow from that will emanate away from the convection that produced it. And then forecasters can track where that outflow boundary is located. And in some cases, the outflow boundary can be a little mini cold front, if you will, a gust front of sorts, and therefore can produce upward motion and may contribute to the development of other convection. And these outflow boundaries actually lay around and persist into the next day, and forecasters can track where those are, and they can be the focal point of the next day's round of convection. And of course, you have frontal systems such as a cold front, a warm front, stationary occluded fronts, and then also don't forget the dry line here on the lower left. Usually a dry line is a separation of not air masses. Usually you're dealing with warm, moist air, especially in Texas and up into Oklahoma, and then the other side of the dry line tends to be very hot, dry air. So it's really more what they call a dew point line rather than a front itself. So a dry line can contribute to pretty significant amount of convection because it is a density discontinuity that can provide the necessary ingredients for development of thunderstorms. And then last but not least, you'll see something called a surface pressure trough. And unfortunately, that looks remarkably like an outflow boundary or even the intermediate isobars, but it's actually a surface trough. It won't be labeled as a surface trough. It just won't have any label associated with it. And that's essentially the guidelines that they use. I know not very friendly, but essentially that's the way it's depicted. So a surface trough is just really an elongated area of low pressure. It doesn't have really any distinct low-level center. No surface low pressure system as a result of it. And again, think about you digging a trough in your backyard to bury a pipe. It's a pressure trough in this particular case. It's a divot or a low spot in the pressure area, and forecasters like to point that out. Frontal systems actually are also surface pressure troughs, but they separate air masses. So frontal systems separate air masses, but pressure troughs do not. They're not a separation of an air mass. And if the air is on the drier side, which it typically is in these situations, most of the time a pressure trough will have little or no significant weather associated with it, and usually is pretty harmless in most cases. So similar to a front, a surface pressure trough is actually a situation where you'll have convergence. And you can see here, in this particular case, that the winds here are essentially out of the southeast or south on the east side of this pressure trough, right, shown right here. And up here, you'll see the winds are more out of the west or northwest. Very similar to what you see in a frontal system, and that's where you see the air is going to be converging there. If you go out west, the southwest US, that pressure trough out there is pretty much ubiquitous most of the year. We call that a thermal trough, something you'll typically find in the desert Southwest. Again, generally pretty benign. If you look at lee side of a mountain range, you see this a lot on the Rockies, also in the Appalachians, you'll see a lee side trough. Usually, again, generally pretty benign. But during the warm season, when we're dealing with significant weather events, a surface pressure trough can sometimes be the impetus for the development of that deep moist convection or thunderstorms. Because again, surface pressure trough represents an area of convergence. So this could be a situation where we may see the air converge and help or enhance the ability for air to rise. And essentially, if the air is unstable in that region, it may again contribute, but it's again not something that we typically see. As you can see in this pressure trough, look at all the station models here. All are completely empty, meaning there's no clouds associated with any of this area, and there's certainly no real weather anywhere in this region either. So, and this is not a weather maker on most situations. So another question we got was, how do I know if a METAR includes wind shear? Well, first of all, let's define what wind shear is all about. So wind shear is a marked change of wind speed and or wind direction by definition. And so the wind can change direction and speed vertically as well. So you see here on the lower left, this is horizontal wind shear, where we see the wind changing speed or direction on a specific horizontal plane. But the same thing can occur vertically with vertical wind shear, where you have it change in speed and direction with height. Both of these happen, and sometimes they happen at the same time. So a surface observing system like an AWOS or ASOS can't directly report wind shear. So if you look on your METAR, your for special observation, you're not going to see a METAR reported. It can, however, be reported in an ATIS broadcast. You'll see something like wind shear advisory is in effect. But as far as the actual report itself, you will not see wind shear being reported. However, they do have the capability at some airports, developed in the 1970s in response to several aviation accidents that were fatal in the commercial world, a low-level wind shear alert system. These are sensors that are spread in different parts of around the airport, usually again larger commercial airports, that can alert controllers when anytime there's a wind shear event occurring. And so the controllers can then relay that to the pilot or the crew to let them know this is happening. Again, if you go to all the major airports that typically will experience wind shear events, you're going to find this system installed. But we have no real-time access to this information. It all comes through controllers. So low-level wind shear alerting system doesn't get reported in an observation like you might see wind speeds or gusts reported. So anytime you see strong and gusty winds in an observation, that's probably your biggest clue that there could be some low-level wind shear occurring. And obviously, anytime you're dealing with the possibility of convection, low-level wind shear is almost by definition a part of the sense. So if you see a METAR reporting a thunderstorm, most likely you're dealing with low-level convective wind shear in association with that, and even the possibility of showery precipitation as another indication that you have a convection going on at that airport. So we generically call this convective wind shear. You may say, I've seen wind shear forecast in the terminal aerodrome forecasts. And you're right. It's called non-convective low-level wind shear. And that can sound very scary But note that non-convective low-level wind shear, as you'll see it in the TAF, is not a forecast for turbulence, and certainly not a forecast for turbulence associated with convection, because it's called non-convective low-level wind shear. So let's take a look at this a little more carefully. So if you were to see something like WS020/16055 KT in a terminal forecast, this literally translates to the winds at 2,000 feet above field elevation, in this case 020, so that's 2,000 feet, are 160 true at 55 knots. So it's basically telling you the wind speed and direction at the top of that wind shear layer, in this case, 2,000 feet. What this forecast implies is that the wind rapidly increases with height within that 2,000-foot wind shear layer. And so essentially the 160 at 55 knots gives you the magnitude of the winds at the top of that wind shear layer. So we call this a form of vertical speed shear. Yes, the winds can change direction in that as well, but this is usually equated to wind speed changing with height, increasing with height over a short altitude span. And you may also find something called a low-level wind shear GRmet. And that, again, it's a non-convective low-level wind shear forecast that's forecast over an area. And it's typically for the GRmets that you'll see, it's in the first 2,000 feet. So what this tells us, within that depth of that wind shear layer, how the wind speeds are changing with height. So in this case, where you have a 020, that's the depth of the, in this case, 2,000 feet of the wind shear layer. Then you have the winds at that particular altitude of 160 degrees, that's 55 knots. It shows you how the wind speeds are increasing. Of course, this is just an example. Winds could be fairly strong, still pretty strong at the surface, but essentially what you're seeing is the wind speeds rapidly increasing with height. And again, that's called non-convective low-level wind shear. So you might think, well, if that's the case, the winds are rapidly increasing with height, you might see in this particular case that maybe the air is rotating like a tumbleweed would over the ground. The problem with that is that this develops when the atmosphere near the surface in that wind shear layer is incredibly stable, usually courtesy of a temperature inversion. And so when you have that temperature inversion, which is a very stable atmosphere, it tends to inhibit any movement up or down. So anytime the air wants to move up and rotate, like that tumbleweed, the atmosphere tamps down that particular motion, or the other direction, whether it's up or down. And essentially what you end up with is very laminar or non-turbulent flow. And the air is basically said to decouple from the surface friction. And if it's decoupled from the surface friction, it's free to accelerate. And so what we get typically in these situations is what's called a low-level jet. Air doesn't really feel the ground and feel the friction because air doesn't move up or down. So that air just above the surface is free to accelerate unencumbered by the surface. And that's where you get the acceleration of the wind with height. So hopefully some of you remember the Mythbusters program. There was an episode called Bubble Trouble, which I think explains this pretty well. And that is Adam and Jamie built a 4 by 16 foot bubbler with a massive compressor, and they placed it at the bottom of a swimming pool. Then Adam gets in the pool and attempts to swim across that particular area where the bubbles were coming up from the bottom. And so you would think, if I'm in that pool and I'm trying to swim through all those bubbles that are coming up, it's going to make it more difficult to swim across the pool. And what they found is that if they put the compressor on 25% power, it proved pretty difficult for Adam to swim across that. But as soon as they cranked it up to 100% power, he could not swim across those bubbles, entire length of the pool. It slowed him down. And so when you think about this non-convective low-level wind shear, what we typically see in the atmosphere is that we see air rising. So the air is rising up like the bubbles in that compressor. And that prevailing wind has to interact with that thermal, that rising air. And as a result of that, it tends to slow down, inhibits that prevailing wind. But what happens if I take that thermal away? What happens if I make this situation very stable with no rising air or falling air? Well, it's just sort of like swimming across the pool without the compressor on. It produces very laminar flow. And therefore, that air is free to accelerate unencumbered by surface friction. And so that's essentially what non-convective low-level wind shear is all about. And so you can fly through that and may not even notice that it exists. In fact, we see this happen frequently in the overnight hours in many cases where the atmosphere is very laminar. The winds aloft can be screaming along at 40, 50 knots, 2,000 feet above the ground. And unless you notice the ground speed on your GPS, you probably won't even know it's there. It's so common that they don't tend to forecast it in the overnight hours. But when you see it forecast in a TAF and it's coupled with rain showers or thunderstorms even, yes, you can have convective and non-convective low-level wind shear in the same line in the TAF. That's when it can become problematic here. And the reason is that as that strong, especially when we start getting up into the 60s and 70 knot range, think about that wind that's flowing 2,000 feet above the ground. You have a heavy rain shower that pushes down through it, and it can turn that 75 knot wind straight down to the ground, producing a downburst or a microburst even, which would ruin your day if you're on short final. So when you couple this with a showery precipitation or even thunderstorms, that's when you want to pay close attention. You probably should avoid flying in those particular cases. The other question we got is, how is surface wind forecast? And kind of what makes it strong and gusty on some days and steady on the other. Well, surface wind, as you might expect, is a really difficult, of all the sensible weather elements we deal with, like temperature and dew point, surface wind is really difficult to predict reliably because it typically is affected by local terrain. Really, really hard to predict something that's on a small scale like that. So ultimately, we can't necessarily predict every kind of wind gust that may occur at an airport. We try to do is give you the understanding of whether this particular case and the magnitude of the wind and the direction of the wind. And we do that through, as meteorologists, through a variety of different methods. Some of the guidance that forecasters use comes from basic experience. A lot of the terminal forecasters that are positioned around the country, they understand the local effects. They know where the airport's located. And as a result, they can forecast for the airport pretty well. You can also look at numerical weather prediction models. They do a pretty fantastic job, especially in the short term, of predicting what the wind is going to be like in terms of speed and direction. And also maybe MOS, model output statistics. Model output statistics are great because they use what's called geoclimatic data. So they use historical information from the particular airport. So when they get the weather forecast model to predict, they can look at that information and they can use the knowledge based on that particular airport's geoclimatic situation. So if it's up on a hill or down in the valley or next to an ocean, that's going to affect what the wind is like. And because it's using historical data from that particular airport, it does a fantastic job of producing, especially in the form of wind forecasts. If you were to look at, for instance, some of the various different forecast models out there, and you can go out and look for the high resolution rapid refresh model, it does a fantastic job because this particular model has a 3-kilometer resolution. So that's 1.86 miles. So a very fine resolution, which from a standpoint of a pilot, that's on the scale of the size of the airport itself. And you can see here that you can see the wind speeds showing up here as well as wind direction showing up. Again, this is at the surface, or possibly in this particular case, it's the 10-meter wind. So it's not really right at the surface, but 10 meters or about 30 feet up, which gives you, again, a good indication of what to expect at the surface in terms of wind speeds and potentially gusts. You can also, again, look at the Localized Aviation Loss Program, or LAMP, which is a different spin-off, if you will, of model output statistics. Again, it can show you where the wind is the strongest. So in this case, we're dealing with wind gusts once again, and you can use the legend on the left in this particular case. I produced this particular chart from my own website, but you can actually go out and look for Localized Aviation Loss Program, or LAMP, and they will provide that to you there as well. Again, this is wind speeds and wind gust over the next 24 hours or so. So it provides really good guidance at a big weather picture, if you will, for wind gust and wind speed. And it's in this particular case, the MOS forecasts are done at individual airports, but then they can grid this over the entire country. And then you can also see an airport-specific forecast. Some of the various different heavyweight apps out there do provide that. As we discussed earlier, temperature differences drive pressure, and pressure differences drive the wind. And so at first glance here, you might think areas where there's high pressure gradients, you'll see very strong winds. So we have a high pressure gradient up here near this area of low pressure, and you can see the wind barbs are showing pretty significant winds, 30, 35 knots. That's the prevailing wind. That's not even the gust factor added on. And they, again, should be higher there. But let's take a look at the area. Let's just go back real quick and look down here where the wind speeds are, or the isobars are pretty far apart here, but you still see pretty good wind speeds. So there you go. So we still see wind speeds 20, 25 knots in many areas where the isobars are pretty far apart overall. So just because the isobars are close together, that typically means you'll be dealing with higher wind speeds, but because they're farther apart, doesn't necessarily always equate to that. And one of it, you have to look at essentially how winds and why winds gust. So if we look at what's called the planetary boundary layer, that's the area of weather that's typically within the first several thousand feet, maybe as much as 5,000 feet. You go out west in Las Vegas area, it could be as much as 15,000 feet. But essentially, that's the area that we're concerned about here. We have essentially what's called the surface layer. That's usually within 500 to 1,000 feet above the surface here. And then we have what's called the mixed layer, where we get most of the mixing, most of the thermal turbulence that's occurring there. Then we have something called the entrainment zone, which is the part that we get into the free atmosphere above. Because we get into this mixing that's going on here, essentially look at this in this particular case, what we see here is that the atmosphere essentially mixes or makes it more homogeneous in terms of the wind speeds. The length of the arrow is the wind speed. So we notice that the wind speeds increase and then they kind of stay the same in this mixed layer. And then they get stronger as you go aloft. So this is the layer that we typically start to look at if we want to estimate what the wind gusts would be. So we typically find the top of that boundary layer, and that can tell us essentially what the strongest winds at the surface could possibly be in the form of wind gusts. So on days where the atmosphere is kind of unstable, where you have a lot of heating going on during the day, that may be actually the result of, again, thermals being produced. So essentially what goes up, something's got to come down to replace it. So you can get essentially some air that's rushing down underneath these that can produce very gusty winds. And where does that come from? Well, that comes from essentially the top of that boundary layer. So we call that mixing down. So the stronger winds at that top of that boundary layer mix down to produce those gusty winds. Notice here, I really didn't tell you that whether or not we're dealing with a situation where we have a high pressure gradient or a low one. In most cases, we can see this even in places where the pressure gradient is pretty minimal, but still have a fair amount of gusty winds, 20, 25, not gusts that come down. So look at that top of that boundary layer. Look at about 5,000 feet up above the ground and look at the wind speeds there. That's probably going to be the maximum gust that you're going to produce. So what is the most reliable way to know cloud tops? Well, I think it's using pilot reports. I know that's a cop-out, but when they're available, typically they provide the best choice, the most accurate choice. But they are referred to by mean sea level height. So in this case, you can see that's pilot weather report. Tops are 5,000 feet. 050 means 5,000. And even some other interesting things like top is ragged with a higher layer above is important to include. You can also use satellite imagery. So you might also use what's called echotops if there's precipitation occurring. That comes from your NEXRAD. And also something called a VAD wind profile, or VWP. And again, that comes from NEXRAD. And if you're really techie guy or girl, or you like the details of getting your hands dirty, look at the SCUT log P diagram can also help. But it really depends on the type of clouds that are present. Stratiform clouds, real simple. They're really easy to figure out. I could teach somebody typically in maybe less than 10 minutes how to figure out where the tops are. Cumuliform clouds, on the other hand, can be quite problematic because you can have all sorts of different conditions that produce clouds at all different altitudes. Really hard to know for sure in many cases. But if you use the color-enhanced satellite imagery, which they unfortunately took away from the aviationweather.gov site, but it's out there. If you go to the UCAR site, you can actually find this out there as well. Again, stratiform clouds are fairly easy to find out. Cumuliform clouds, even on this chart, can be very problematic. So what you would do is you look at the satellite image, and the satellite image here, the color that you see is the cloud top temperature. It's the temperature of the cloud top, or in some cases, the temperature of the surface of the Earth if there's no clouds there. So you find the color, whatever that happens to be, and you match that up. In this case, I'm looking at this pale green color, -20, and you match that up to the winds aloft forecast for the essentially what the height is of that particular temperature, and there's your cloud top. Or you can also use the SCUT log P diagram. Really quickly, you can find the temperature and dew point where it's spreading apart. And again, that's probably located, or that's probably where the cloud tops are located, whether it's a radiosonde observation or using a forecast model for what's happening in the near future. And another approach here is the VAD wind profile, which comes from the NEXRAD sites. This is available through the Plymouth State Weather Center. And kind of you're looking at here is a volumetric sensor area. So it's not right at a specific location, but it's more of a volume area around the NEXRAD site. If there's not ample moisture out there, you're probably not going to see this tell you much. But if there's a fair amount of moisture, what you're going to look for is the ND, where the ND means it's no detection, meaning nothing above that. So essentially, you can kind of say that maybe the tops are here right around 8,000 or 9,000 feet in this particular case. And this is a time series graph. You can see the time shown here at the bottom. And if you fly with SiriusXM, you may be able to see the echo top heights. So I'm showing this here on a G1000, and it's shown by shades of gray, and you can put the cursor up and you can cursor over it, and it'll show you what the echo top is right there. Again, it has to be precipitation in that region to know where the tops are. And this is the echo top, not necessarily the cloud top. So what's the difference between composite and base radar? Again, a very common question I get. Well, the NexRads basically scan the atmosphere using 360-degree sweeps, multiple sweeps around from elevations as low as negative 0.2 degrees all the way up to 19.5 degrees. We call that a volume scan through all those. And we know the radar, it's a forward-pointing pencil beam radar. It sends out a pulse of energy, and that strikes various airborne objects. Typically, those that are associated with weather are called hydrometeors, like raindrops or snowflakes, hailstones, ice pellets. And the radar then listens for that backscatter radiation, and they measure that in the reflectivity parameter of Z, and it's usually recorded as decibels of Z or dBz. And at your next hangar party, you can put out some trivia out there and say, in 1 hour, the radar is on for about 7 total seconds, but it's doing an incredible amount of listening for 59 minutes and 53 seconds. So the radar is really doing more listening than it is sending out a signal. And so every elevation scan from the lowest all the way up to the highest all produces what's called a base reflectivity product. So you may have been taught when you say, hey, I want to look at base reflectivity, you think it's lowest. The term base does not mean lowest in this particular case. That's because every elevation scan has base data associated with it, whether it's reflectivity data, velocity data, or what's called spectrum width. All these have base data associated with it. It turns out that most of the ones that you look at, either on the internet or on your favorite heavyweight app, they usually show the lowest elevation, and they usually call that base reflectivity. They really should call it lowest elevation angle or lowest tilt, to be clear. So again, 2 reflectivity products we generally look at here. One is called composite reflectivity, which is essentially the maximum in a column of air. So you start at the surface and go all the way up to the top, and whatever the maximum reflectivity value is from all elevation scans in that volume, using all the possible elevations, that's the reflectivity that's used. So it's the worst case scenario, if you will. Whereas base reflectivity from the lowest elevation scan, the lowest tilt, is usually kind of representative of what's falling out of the base of the cloud, because that's the lowest scan that the radar sees. And so when you're looking at composite reflectivity versus the lowest elevation angle, what you generally see is that the composite has a much larger footprint to it. Essentially, what's happening here off the coast of Florida is that in this particular case, the composite actually will see some of the ice crystals that are in the storm's anvil. We see that fairly frequently. Sometimes not necessarily useful to us. We're not flying up high. If we're flying down low, we really don't care what's out there. But you should always, in many cases, be looking at both. So I always tell folks that typically when you're looking at the base reflectivity, the lowest elevation, that usually represents a really good, it kind of matches pretty well with what you see outside the cockpit. So you can see where the individual cells are. So flying in this particular region where you see those higher ice crystals in the anvil probably is not going to be a problem for you to fly in that region overall. But also you have to look up here where you see there's an area where the base, and then you see the composite, where you actually see what appears to be that the precipitation core is elevated. So the radar itself is essentially at the lowest elevation, is not seeing that. It's seeing what's happening higher up. So in those particular cases, it's always best to kind of be looking at both of these, but the base is going to be more representative. Again, it's going to meet the sight picture, what you see outside the cockpit, especially when you're flying down low. Okay, so we are at the point where we can take any questions. Here's my Website, EZWxBrief.com. There's my email address if you want to email me directly, or if you're interested in purchasing a SKUT book, you can go to adwxtraining.com/SKUT.